In this video, we're going to look at some common resonance structure. And one common resonance structure has 18 electrons. I'm going to do SO2. If I look at this, S has 6 valence electrons, each O has 6 valence electrons. So 3 times 6 would be 18 electrons. If I look at this structure here, 2, 4, 6, 8, 10, 12, 14, 16, 18. This one also has 18 electrons. It's got a little sloppy, so there's no electrons there. That's just smudge, and this should just be an electron pair at top. So I should have been more careful with that. Make sure you're careful with those things so you clarify what you need to clarify. Okay, I think I'm just going to go with showing how I got this structure. And it's a little bit of trial and error, and there are different ways to do this, but I'm just going to show one method for that. So I'm going to go to a draw function. And let me see, grab my marker. I'm going to put sulfur is the central atom. Okay, it's the least electronegative. There's only one of them. And what I think I'm going to do is just do little lines for electrons. Sorry, that might be confusing. I really have a hard time writing in these dots here. So I got this right here. So that is sulfur at 6 valence electrons. It looks like it's going to combine with a couple oxygens. Maybe I'll change my marker and put my oxygens in here. And we'll go O, and oxygen has 1, 2, whoops, that looks more like a point. Let's do that, still a point. Okay, 3, 4, 5, 6. Oh, I didn't quite fill the octet. This is dangling by itself. Let's do another oxygen. I might just start here. 1, 2, 3, 4, 5, and 6 right here. Sorry, that one's kind of squiggly, but I think we get the idea. Okay, so it looks like I got an extra electron right here. I got 2, 4, 6, 8, 10, 12, 14, 16, 17, 18 electrons. So this is right. However, I don't have an octet around the oxygens, and so it's not matching up. So when I'm short of electrons, I think, oh, I need to double bond. So what I'm going to do is actually take this electron and one of these electrons right here and double bond those. Maybe we'll go to a new marking right here. And I'm going to move an electron here. And I didn't change the color, an electron here. So what I did was I took this electron, try to get this right here, away here. And I took one of these electrons right here, not both of them. All right, so I'll bring one of these back. All right, so I got 2, 4, 6, 8, 10, 12, 14, 16, 17, 18. Okay, now this oxygen's looking pretty good. I got 2, 4, 6, 8 around this sulfur. It looks like I got to get rid of this electron. This one needs an electron. So I'm just going to bring this electron from up here and put it down here. So I'm going to write this one down here to fill that up. I'm going to erase this one up here. And it's a little bit of a trial and error is what I did. But ultimately, I have 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. I have 8 around this, 8 around this, and 8 around this. So this is going to be our structure for this right here. Notice these two things do compare as we have an unbonded electron pair, a double bond, and a single bond. At least that's what it looks like. So this is going to be our structure that looks like this. It's a plane with S in the middle. Assume where my hand is an electron pair, and then there's 2 oxygens with the other white one. So there's an S in the middle where my hand is an electron pair, and then the 2 oxygens are the other 2 outer atoms right there. Okay, it looks like this is a double bond and a single bond, but it's actually like a 1.5 bond between each. There's a sigma bond between sulfur and oxygen here. There's a sigma bond here, but the pi bond is free to float. It's still localized above and below the plane and equally dispersed between these two. Same things right here. We can't really show that with a drawing. So what we actually do is just try to show a resonance structure, really multiple structures showing one concept as a hybrid, and that's what we're showing. So if I ask some questions, the shape again is going to be bent because it looks like trigonal play where one of these is an electron pair. The bond angle is going to be 120. These electron pairs take up a little bit of extra space, so it might be slightly less than 120. The hybridization is sp2, 3 letters, okay, because of 3 electron domains. It is polar, okay, it's more negative toward the oxygen, so it's going to be polar with the arrow pointing this way. And its bond order is 1.5, okay. It's stronger than a single bond, weaker than a double bond. It's actually right in between with a bond order of 1.5. Now notice NO2 minus has 18 electrons. It's going to have a similar structure, except this extra electron will go into place. O3 is another one that has a similar structure like this. Notice I could take HNO2 and it's going to be like this structure, but then we're going to have to attach an H to one of the O's. So that's going to change things up a bit. But knowing this base structure of 18 electrons, I think is real helpful for a lot of the other things you're going to see. Let's go to the next example here. And this is going to be SO3. And again, we have a resonance structure. It's not single bond, double bond. Okay, notice I changed where the double bond is, okay, or where the double bond appears to be, but I'm putting it in the 3 different spots. It's really like a 1 1/3 bond here. This is a 1 1/3 bond. This is a 1 1/3 bond. And we have 3 structures to represent that. Okay, so what happens is we have this shape again, it's trigonoplanar. This time there are 3 oxygens on it. So that will be the shape trigonoplanar. There are 3 electron domains, so it's sp2. The bond angle will be 120. Okay, it'll be nonpolar because the dipoles all cancel out. And the bond order is what? 4 bonds over 3 electron domains would be 4/3 or 1 1/3. All right, the last thing is I think I'm going to end up drawing this structure kind of by the trial and error. So it is bigger, so it's going to take a little bit more time. And I'm going to do the little dashes again. Hopefully I can do a little bit better there. Sulfur, sulfur. So these little lines are supposed to be electrons, and it's just really hard to do it with this to figure out what's going on. Okay, so this looks like it has 2 places to bond to. So I might throw in some oxygens. Let's make this blue. All right, so I'm going to do an oxygen right here. And oxygen has 1, 2, 3, 4, 5, 6. So there's an extra one left over. Saw that before. Still needs to bond there. I'm going to just start here and go 1, 2, 3, 4. Okay, that's already bonded, so I'm not going to mess with it yet. 5 and 6. So we're 1 short there. I got to get another oxygen. Both of these are paired up, so I'm just going to do this. Again, this structure doesn't really tell you where it comes from, so we're getting a little unconventional. I'm going to pair this up and just double check. Looks like I got 2, 4, 6, 8, 10, 12, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. I have 24 electrons. It looks like I'm short here, and this one looks okay. When I'm short, I think I need to double bond. So let's go to some different structure here. So I'm going to move an electron from here over here. So I'm going to move this one over and give it a new color. And I move one of these down here and do that as well. So what I did was I removed this one and I removed one of these 2 right there and put it down here. So I got 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 21, 22, 23, 24 electrons. The other thing is, oh, this looks like I got an extra electron. This is short of an electron. So I'm just going to erase this one and draw it down here. I know it seems unconventional and there are different ways to approach this. But ultimately, this is what we should end up with, a 24 electron structure. 1 double bond, single bond, and a single bond. Notice 8, 16, 24 electrons total, and everything matches to the octet rule. All right, I think we talked about how this will look with shapes and things. Notice NO3 minus, CO3, the carbonate ion minus 2, all have the same number of electrons. They're all going to have similar structures like that. So 24 electrons is another common type of electron dot structure. when you get in biology, or if you're in biology, or if you've had biology, you're going to see this. This is a benzene ring, or when it's attached to something, it's a phenyl group. Okay, and really what it is a series of alternating single double carbon bonds. I'm going to bring a picture of this one right here, but it is a planar structure. Okay, it is in this shape around each carbon. If you look, trigonal planar. Okay, is this really a double bond and a single bond? No, it's like a 1.5 bond all the way through that rides above and below the plane. So if I look at this structure, it might be drawn here, or I could switch where the double bonds are as a resonance. And because this is so often used in biology, we have a shorthand for this just with the ring around it. And every corner represents a carbon, and we fill up enough hydrogen so it has 4 bonds. So we know what that is a benzene ring. Let's see, just a little bit with that structure. It's trigonal planar around each carbon. Okay, you have a ring. Ultimately, dipoles cancel, so it's nonpolar, and its hybridization around each carbon is sp2. Its bond angle is going to be 120, and its bond order is going to be 1.5 around each carbon, right there. All right, hope that helps with some of the common resonance structures you will be seeing. Thank you.